Namaskara Karnataka students, this is your Captain Shreyas, and since your midterm examinations or your PU board examinations will be round the corner, so I thought of quickly going through all the important concepts, the most high weightage topics in your physics midterm examination for your PU Karnataka board. All right, so let's quickly dive into this and make sure that you are liking this video and share this video with your friends as well, so that everybody who is preparing for this examination gets benefited from it. And of course, it is Nama channel, Nama Karnataka channel. Make sure you are subscribing to the Vedantu Karnataka KCT and boards channel as well. All right, so let's start with the most important concepts right from Ohm's law, resistance, drift speed, Lawen forces, and the different kinds of motion that you can get, and as well as the Ampere's law. So I have seen that many times these questions, these concepts are repeated in your board examination. I will show you the concept, I will give you my handwritten notes, as well as I will show you the sample questions as well. Okay, so when we start off with the first concept, which is Ohm's law, it tells me that if I pass some current inside a conductor, that current depends on how much voltage I apply and the resistance of that particular wire or that conductor. What is a conductor? It is something which conducts, allows the electricity. The opposite of a conductor is an insulator like rubber, wood, which does not allow electricity. Metals, usually like copper, aluminum, gold, they allow the passage of current. So when I connect a battery whose voltage is some V volts, maybe you take a pencil cell of 1.5 volts, or you connect some higher voltage, let's say 12 volt battery from a scooter, and you pass it through the wire, how much current goes depends on the resistance as well as the voltage. And if you draw the graph of how much voltage you have applied versus how much current passes, that graph is a straight line like this. Who said this? Not me. Ohm said this, and many hundred years back he discovered this law. So he saw voltage is proportional to the current. More voltage, more current. Less current, less voltage. And that constant of proportionality is called as resistance. How much does it not like the current to pass is the resistance. This is the symbol of a resistance. Any conductor will have some resistance. This is that particular symbol. And voltage is measured in volts, current is measured in amperes, resistance is measured in ohms. Okay, so that's the unit of it. As you can see in this particular graph, since the voltage increases when the current increases, if the graph is more steep, that means there is more resistance. Reason being, you can see for that same current, I need more voltage. That means I need more energy. So the resistance is higher. So if the graph goes here, more steep, more slope, then the resistance is higher. If it comes down over here, then the resistance is lower. I hope this concept is absolutely clear. But remember, Ohm's law also has some limitation. Like every student, every teacher will have some limitation. Same way, the limitation is that this graph, which is a straight line, is not always true. Only certain devices obey this law. Those devices like metals, they are called as ohmic devices. Ohmic devices follow Ohm's law. There are devices where the graph is not a straight line like this. It could be some curve like this diode, which you will study in the last chapter of your physics, or even some combination compounds like GaAs, where the graph of voltage and current is a weird looking non-linear. Linear is a straight line, non-linear means it is curved. Those devices are said to be non-ohmic devices. But don't you worry, in our syllabus we have to study mainly ohmic devices, but you should know the graph and the limitations of Ohm's law, and you should know these graphs as well, because there have been many questions on this. Next important thing, sir, how do I measure the resistance, sir? if I don't know the voltage and current? Well, if you know what is the area of the wire through which the current passes, and if you know what is the length of that wire through which the current passes, then the resistance is found to be proportional to the length. More the length, more the resistance, and it is inversely proportional to the area. If it is a big wire, it has less resistance. If it is a thin wire, then it has more resistance. So resistance proportional to the length, resistance inversely proportional to the area. That constant of proportionality is called as rho, which is defined as resistivity. Resistivity is the characteristic of a material. Meaning, if I take a copper wire of different lengths, different sizes, they will have different resistances. But what will be common in all of them is they will have the same resistivity, because it is a dependent quantity on the material and the temperature of the wire. So, all copper at the same temperature anywhere in the world will have the same resistivity. The resistivity will be more if it is not a good conductor. Understand that. If it's a bad conductor, it does not allow electricity so much, it will be having higher resistivity. Lower resistivity means it conducts more. Like silver is a better conductor than copper, and copper is a better conductor than aluminum. So silver will have very less resistivity, or I can say it has better conductivity. Copper will have slightly more resistivity. Aluminum will have even more resistivity. In fact, there is a term called as conductivity whose symbol is sigma, which is exactly the reciprocal of resistivity. More resistivity, less conductivity. Less resistivity, more conductivity. It is exactly inversely related to each other. The unit of resistivity is ohm into meter. You can get it very easily by shifting the units, which you would have studied back in 11th grade, units and dimensions chapter. I hope this point is absolutely clear. Okay, so that is resistivity and the length and the area of that particular conductor which decides the resistance. The applied voltage and the resistance together decides the current passing through the conducting wire. Okay. Sir, what is the exact nature in which the resistance changes with temperature, sir? Well, here is the formula. At any temperature, the resistivity is given by resistivity initially, rho naught, into 1 plus a constant which is called as coefficient of thermal resistance into the difference of the temperature. Maybe when the temperature T naught is 0 degrees Celsius, maybe the resistivity is some value. At some new temperature, maybe 20 degrees Celsius, I want to find what is the new resistivity. So that's when you use this formula. If you remember correctly, this formula is very similar to the formula which you have learnt in thermal expansion in 11th grade. The final length of the rod is initial length of the rod into 1 plus alpha delta T. But there alpha was coefficient of linear expansion. Here it is the coefficient of thermal resistance. This alpha, don't worry, it will be given to you. If it is not given, that means other things will be given to you where you have to find alpha. So alpha decides how quickly it will change the resistance with temperature. There are some elements which slowly change the resistance. So for them alpha will be less. But for others, alpha is more, means if you change the temperature even slightly here and there, the resistance will go up or down very quickly. So it decides how sensitive the material is to the temperature. Now, this equation is not always valid. It is only valid if the temperature changes are minimal on a small range. If you change from 100 degrees to 1000 degrees, don't expect this equation to be valid. So it is valid for maybe 20, 30 degrees or 50 degrees, maybe 100 degrees here and there, but not more than that for a decent range of temperature. In fact, that can be seen through these graphs. As you can see over here, for nichrome, surprisingly, it is a straight line for most of the temperatures. So the resistivity changes with temperature linearly. Good. That means I can use this formula for a longer range. But for copper, you can see it is a curved line. That means only for a small range it looks like a straight line. So only for small ranges of temperature, I can use this formula. Don't worry, in the examination hall or your paper, you will get only small ranges. Nobody is going to give from 0 degrees to 2000 degrees. It will be like 100 to 250 or 20 to 80 degrees, those kind of temperature ranges. One weird thing which happens is for a semiconductor, which you will study in the last chapter of physics, where the resistivity, instead of increasing, it decreases as the temperature increases. The reason for that you will study there, but for now you should know this is an exception. Usually for our conductors, as you increase the temperature, what you will find is the resistance also increases, because there will be more collisions between the atoms, the electrons, so it will find it difficult to allow the current to flow when temperature goes up. So that's why for usual conductors, the resistance increases as temperature increases. But for semiconductors, which we will study later, but only the conclusion which you should know is resistance decreases as our temperature goes up. All right. So these were some of the questions which have been asked in the previous years with the years that I have mentioned. You can see most of the questions are exactly based on the concepts that we have studied, and you can expect these kind of questions in your midterm board examination. Going ahead to the next concept, I hope you have smashed the like button. In case you have forgotten to do so, make sure you do that. And if you have not yet subscribed, subscribe to the Vedantu, yes, Karnataka channel. Next important thing, my dear warriors, is the concept of drift speed. Now, when current moves inside a conductor, it is basically these electrons which are moving. If the current is going one way, electrons are negatively charged, they are actually going this way. Since negativity goes this way, it is as good as saying positivity is going the other way. If I say the badness in me is going out, that means I am becoming good. Same way, negative charges going here is the same as current moving this way, and current is assumed as the flow of positive charges. That's the historical reason, convention. So these electrons will keep colliding here, there, and they will slowly keep moving, drifting slowly here to here to here. So that average speed with which the electrons keep moving from one side to the other side is called as the drift speed. Symbol for that is Vd. Now this drift speed can be found out by simple logic that whenever a collision happens, the electron loses the speed. Again, it increases the speed, again collides, loses the speed, again increases the speed, again loses the speed. So it keeps on, accelerating, losing, accelerating, losing the speed. So we can find that average using our kinematic equation. Final velocity is initial velocity plus acceleration into time. V is equal to U plus AT. Now, after collision, for an average, the electron will lose that speed. So the average speed initially will be 0. Number 1. Number 2, after colliding, till the next collision happens, there is some time duration. I collided, accelerated, stopped, accelerated, stopped. So that duration between successive collisions on an average is called as relaxation time. Imagine the electron collides, it's like getting one slap. Again one slap comes after again one more collision. So the time between successive slaps is the time the electron is relaxing. Thank God I'm not colliding. Okay, it's relaxed. So again the next collision happens. So that time gap is called as relaxation time. That is your T, which I'm going to substitute. The symbol for that is that weird looking tau, like the torque symbol. It's like one umbrella. Okay, it's a Greek symbol. Okay, I hope this is clear. Next, what about the acceleration? Acceleration is given by force by mass, Newton's law. What is the force on a charged particle inside an electric field? It is charge into the electric field. Charge is the charge of the electron E, which is having the value of 1.6 10 to the power minus 19 coulombs. Is that right? E is the electric field expressed in Newton per coulomb or volt per meter. What is M? Mass of the electron. So force by mass, force is E into E, charge into field, and the mass is there as it is. So we can substitute this acceleration right over here as it is over here. 0 plus anything is that number. So drift speed is EE by M into the relaxation time. That's the drift speed formula. I hope everybody understood this point till this over here. Okay, moving ahead. Is this the only formula for drift speed? No. In fact, there is a better looking formula also. It is current is NVIDIA. Now this is very easy to remember. I'll tell you what N is in a bit. NVIDIA, the graphics card company. If you play games or are interested in the tech gadgets, mobiles and all, you would have heard of this company like Microsoft, NVIDIA, right, GeForce and all that. So remember, current is NVIDIA. NVIDIA, that's it. What is N? See, in any conductor, there are so many charges, so many charges. How many charges are there in 1 cubic meter, in one volume, unit volume? That is N. That is given to you, you don't have to break your head. E is standard 1.6 10 to the power minus 19. A is the area of the cross section. I is the current. I hope this point is clear. Now, I know some of you might be wondering, sir, who gave this electric field, sir? Why did this electric field come? Is it because of the electrons? No, no, no. This electric field has come because you connected a battery. What does a battery do? Potential difference, high voltage, low voltage, positive terminal, negative terminal. An electric field always goes from high voltage to the low voltage. So there is a potential difference which is causing the electric field to go from high voltage to the low voltage. So definitely there is a voltage difference. That leads us to another interesting formula. Ohm's law says voltage is current into resistance. And we just saw previously resistance is rho L by A. In case you forgot, well, it's right over here. Resistance is rho L by A. So basically substituting that over here, resistance as rho L by A, right? I will shift this area below the current. This L which is in the numerator, I will shift it below the voltage. What is voltage per unit length? Volts per meter. Potential difference per unit length is the electric field. So V by L is E. Rho is as it is kept over here. This current per unit area. Imagine how much current is going per unit area tells me the density of current. If through a small area more current is flowing, density of the current is more. If through a large area, very small current is going. So the current is spread and it is not so dense. The current density will be less than. The symbol for that is J, which is current density, which is I by A. The unit of it, obviously, ampere per meter square. And it is a vector quantity. Whichever direction the current goes, that is the direction of the current density vector. Keep that in mind. Okay, so that's why you get this formula. E is equal to J rho. But you can do one small modification in it. This is very similar, by the way, to V's IR. Instead of voltage, it is voltage per unit length, which is field. Instead of current, it is current per unit area, which is current density. Instead of resistance, you have resistance per unit length per unit area. So that is resistivity. Great. So shifting the resistivity slightly onto the other side, it will become 1 by rho. What is 1 by rho? 1 by resistivity. More resistance, less conductivity. Less resistance, more conductivity. So this is your conductivity. So E sigma is equal to J becomes your next additional formula where you have again many questions based out of that. Next important thing you will be asked is how do you relate the conductivity with the relaxation time? The derivation for that is very, very easy. Observe this, current is NVIDIA. Remember the graphics card company? The current flowing through our graphics card, NVIDIA. Okay, so let's start with that. Current is NVIDIA. Small modifications we are going to do. Take this area below over here, I by A. What is I by J? Current density, how dense the current is, ampere per meter square. Drift speed, I think we just discovered that over here. Vd is EE by M into tau. Okay, so let's substitute drift speed as EE by M into tau. Great. Next step, I hope you can see over here, there is one E. This E was written as it is. E into E is basically E square. So it will become N E square, this E as it is, this tau as it is, this mass as it is, current by area is J. Okay, what's the next step? J, we just discovered over here, is E sigma. E sigma, J is equal to E sigma. Okay, J is equal to E sigma. This E and this E will cancel. So what is left? Rho, N E square by M. and this relaxation time. So conductivity is number of charge carriers per unit volume into the electron charges square by the mass of the electron into the time between successive collisions, which is also called as your relaxation time. This is another important formula which you should know, and as you can see, so many times similar questions. Define Ohm's law, define drift speed, find the drift speed, derive it in terms of relaxation time, define conductivity, find resistivity and conductivity's relation, or how is conductivity related to relaxation time. Same questions again and again repeated in your PU examination. Okay, and obviously questions are also given where n is given, m is given, tau is given, find sigma, or sigma is given, m is given, find n, or t is to be found. So these questions are again very common. All these formulas related to current electricity. Next, going ahead, the next important law in current electricity is your Kirchhoff's laws. Now these laws help you solve any circuit problem which may be series, not parallel, in parallel, combination of series, parallel, any weird circuit. Using these laws you can solve it. Yeah, it might take more time, but if there is no other option, then you can obviously use Kirchhoff's laws. So most common question is about define these laws, show the diagram, show an example. So if the question asks like what is Kirchhoff's laws, then there are two laws. One is junction law, other is loop law. The first law is called junction law or Kirchhoff's current law because it is applicable for a junction. What is a junction? Where things meet, like a railway junction, road junction, node, junction means the same thing. It's a point of meeting. So if you have a point of meeting of wires, some wires carry current this way, some wires carry current that way. At that junction, whatever charge comes in should go out. Nothing is stopping over there, right? So the total current coming inside is exactly equal to the total current coming outside, or basically the net sum of the currents at a node is 0. If 2 amperes comes in, 2 amperes should go out. Coming in, if it has taken as positive, going out will be taken as negative. So if you add them, obviously the total sum of the current at a node or a junction should be 0. It is just based on the conservation of charges. So in this example, as you can see, I1, I2 and I4 are coming in. So currents going in are I2, I1 and I4. The currents going out are I3 and I5. So I3 and I5 are the currents going out. So currents going in is equal to currents going out. That is simple application of Kirchhoff's current law based on conservation of charges. The second law is the Kirchhoff's voltage law. Now, this is also called as loop law because this is not for a point. It is not for a junction or a node. Rather, it is for a path where you again come back. Like you leave from home, go to the school, go to your friend's house and again come back to the home. So it's a loop. It's not like you go to somebody else's parents' house, right? You come back to the same house. Correct. So you start from a point and come back to the same point in that electrical circuit. What are these things? These are some devices. Maybe resistor, capacitor, inductor, battery, wire, this, that, switch, etc. Some things are there. So if you start from here, you will encounter some voltage drop. Some voltage drop, some drop, some drop, some drop, some drop. You add all those voltage differences, you will see the total sum is 0. This is based on conservation of energy. Kinda makes sense. If over here I gain 2 volts, here I lose 3 volts, again I get 2 volts, again I lose some 5 volts, I gain some volts, I lose some volts. When I come back, the total sum of the changes should be 0 because I have come back to the same point. If I increase my volts by 2, I should again decrease it by 2 to when I come back to the same point. Understand that? So it's just based on the conservation of energy. Agreed? I hope this is absolutely clear. And volts is actually joules per coulomb. 1 volt is defined as 1 joule per coulomb. So you can see energy is there in that expression. So if you gain 100 joules per coulomb while going this way, so you should lose 100 joules for that 1 coulomb when you come back to the same point. That's why this law makes sense. Now there is a small sign convention. Sir, these devices are there, sir. When should I know that it is positive, it is increasing? When should I know it is decreasing and negative? I will tell you one simple trick, guys, to remember this. See, if it is a resistor, in the direction of the resistor, you are with the resistance. you are going in the direction of the current in that resistance, it will be a decrease. If you go against the current in the resistor, it will be a increase. So in the direction of the current, it is a decrease, negative of IR. Opposite to it, it is plus IR. I into R, current into resistance is the voltage. So the voltage will drop if you go along the current inside a resistor. Opposite the current, you will increase it by plus IR. But for a battery, it is in fact even more easy. This longer is positive, shorter is negative. If you go from positive to negative, obviously you are going to negative, so negative E. If you go from negative to positive, you are going to positive, so it is positive E. E being the EMF of the cell. Well, if you still did not get it, no issues. I will show you an example. Just look at this particular circuit where you start from this point, go through these devices and you come back. So this is a loop, this is a closed path. R1, I1, E1, R2, E2, I2, some random currents, resistances and EMFs are there. Some batteries are there. As you can see, when you start from here and you go like this, you encounter this resistance and you are going in the direction of the current. In the direction of the resistor being the bad guy, you are with a bad guy, so negative. So minus IR, I1 R1 actually. Here in the battery you are going from the positive to the negative, you are going to the negative, so minus E1. And as you come over here, you are going against the direction of the current, you are going against the resistance, very good. So plus I2 R2. Here you encounter this battery, you are going from negative to the positive, so plus E2. As you come over here, you are going in the direction of the resistance's current. Oh, you are going with the resistor, you are going with the bad guy, so negative IR, I3 R3. Here you encounter this battery, you are going from negative to the positive, so plus E3. As I go over here, I am going against the direction of the current, I am going against the resistance, so plus IR, I4 R4. Lastly, here I am going from positive to negative terminal of the battery, so negative towards negative, so minus E4. The total sum of all of them is a big fat 0. That's how you apply it. As a homework, you can try applying the same law but in the reverse direction. You will see this negative will become positive, this positive will become negative. So that will give a hands-on experience, like a practice for applying Kirchhoff's law. I hope this sign convention, this trick and this example has helped you. As you can see, many times these questions have been asked, and obviously numericals you will get questions on KCL and KVL. Okay, so these were the two important laws. Next is the Ampere's law, which is in your moving charges and magnetism chapter. Now this law is asked many times. Whenever you pass a current through a wire, it produces magnetic field around it. Who said this or discovered this? Oersted. The person who gave the formula for this was Biot-Savart. And these two together, Biot-Savart, they give the Biot-Savart's law. Now, you can find the field using Biot-Savart's law, or you can use Ampere's law to find the magnetic field around a current carrying wire. As you can see, there are many wires which are carrying current over here. There are many wires which are carrying currents over here. Sir, how do I apply Ampere's law? You again start with a path, closed path, which is also called as Amperian closed path or Amperian path. I start from here, I go around those wires and come back. Now when I do that, some of the wires are passing through the path. Some of the wires are going outside the path. So these wires are inside or enclosed. These wires are outside wires. Along this path, as I move, small distances called as DL, and I come back. DL, small distance. At every point, there will be a magnetic field due to all the wires. So this B is not because of inside or outside. This wire will create a field, this wire will create a field, this. All the wires will create a field at every single point. Now you take the dot product. If you remember, work is dot product as force and displacement. Same way, you take the dot product of magnetic field and the small distance. B dot dl, which is B into dl into cos of the angle between the magnetic field and the path which you are going. You do this for every single point and add them up. The meaning of addition, summation is integration. So B dot dl, when you add them up, it is integration. But since I am coming back to the same point, you use this symbol of a circle on that integral, which tells you you are coming back to the same point. If I just put integration, it does not mean that I have come back to the same point. But the moment I put this, that means I have to come back to the same point. That is the symbolic meaning of that over integration over here. Closed path integration. This magnetic field is due to all the currents inside and outside. This whole integration value is mu naught into I enclosed. What is mu naught? Permeability of free space. What's the value of it? 4 pi into 10 to the power negative 7. 4 pi into 10 to the power negative 7 into the enclosed currents. The currents which are within this particular loop, they are called enclosed current. This is called as your Ampere's law. Now, how do I know which enclosed current is positive or negative? There is a simple rule, the right hand rule. If you are going along the path like this, take the fingers of your right hand and curl your fingers as if you are going along that path, as if you are holding that path. If you went like that, you will be holding it like this. Since I am going like this, I will hold it like this. The thumb will go in a direction, that is your positive direction of the current. As you can see, I2 is going in the direction of the thumb, so is I4. I3 is going against. I1 and I5 are outside, so don't even bother. So the enclosed currents are I2 minus I3 plus I4. That's how you substitute that in the Ampere's loop law. I hope this is absolutely clear how to use Ampere's law. Now there are obviously derivations like find the field due to a long wire carrying current at a distance r using Ampere's loop law. So when you substitute everything, you will get magnetic field of a long wire. We will obviously do such things in some other session as well. But I have put those derivations and other things over here as well, because these are the most repeated concepts. State Ampere's law, define Ampere's law. Is the B inside that integration because of inside or outside? It is because of both the currents. Is this enclosed current positive, negative? How do you decide that? Using right hand rule. So these kind of questions again are very, very common. The next concept, which is again very commonly found, is the Lawen force concept in magnetism. In this, let's understand first, if you just take a charge and you apply electric field, the force on a charge due to the electric field is given by Q into E. In fact, this same thing, we also used it right over here in the drift speed, if you remember correctly. The force on a charged particle is charge into the field, Q into E. The Q value was the electron charge value. So coming back over here, yes. So charge into the field is nothing but the force acting on a charge due to the electric field. What happens when a magnetic field is there? The moment a magnetic field is there, there is a force due to the magnetic field. But it is not magnetic field into the charge. The formula is slightly different. The formula is Q into V cross B. It's not charge into magnetic field, that is wrong. It is charge into velocity of the charge into magnetic field. This is a cross product. That means you have to use right hand rule. Velocity is here, magnetic field is here. Velocity cross magnetic field. The thumb will point in the direction of the force. Imagine this in some three-dimensional motion. Okay, velocity cross magnetic field gives me the force. So that force is definitely perpendicular to the field. It's also perpendicular to the velocity. Velocity was here, magnetic field was here. Velocity cross field is the force. So it's perpendicular to field as well as the velocity. Since the force is perpendicular to the velocity, whenever a force is perpendicular to the velocity or displacement, it can't do work, because work is force in the displacement into the displacement. Any perpendicular force, F cos theta if it is theta is 90, cos 90 is 0, it never does work. So this force cannot do work, and when it can't do work, it can't change the kinetic energy. If it can't change the kinetic energy, it can't change the speed. So what does this force do? Only one thing, only changes the direction. So if this force comes, a particle is going, zoop, it will just change the direction of it. But it can't accelerate it, decelerate it speed-wise. So it can't affect the speed, but it can only change the direction, and this is because it can't do work. Why it can't do work? Because the force and the displacement are perpendicular to each other. And the best part is, if the charge is at rest, velocity is 0, the force will be 0. But that is not the case with electricity. Whether the charge is moving or not doesn't matter. If the field is there, the charge is there, it will experience force. But here, there are so many cases where the force can be 0, like velocity is 0, or the charge is 0, or B is 0, and even the cross product is 0. Imagine the cross product is 0, velocity is there, field is there, but the cross product means sine theta should be 0. That means theta is 0 degree or 180 degree. So we'll come to that in a bit in the next slide. But for now, if you combine this electric force and this magnetic force together, the total force what you get is called as the Lorentz force. So there is electric field, electric force is in the direction of the electric field, there is magnetic field, the magnetic force is given by the cross product rule or the right hand rule. So you have the magnetic force, you have the electric force, you take the vector addition of both of them, that net force is called as the Lorentz force. Charge into electric field plus charge into velocity cross the magnetic field. So that is the total force on a charged particle due to any electric and magnetic fields. Based on this, you have three special cases. This is the most important case. This is again important. This is sometimes asked. First case is when there is no force. Like I suggested over here, no force is there if it is at rest. Obviously velocity is 0, force will be 0. But what if velocity is there, charge is there, field is there? Still, can you have no force? The answer is yes. If V is parallel or anti-parallel to magnetic field. Because V cross B, V sine 0 into B will be 0. V sine 180 into B will also be 0 because sine 0 and sine 180, sine 0 and sine 180 both are basically 0. So when there is no force, there is no change in speed, no change in direction. So it will keep on going in a straight line even when there is magnetic field. Okay? Number one case. The second case which you should remember, what will happen if the velocity is perpendicular to the magnetic field? If the velocity is perpendicular to the magnetic field. So imagine the magnetic field is inside and let's say the velocity is here. It will go in a circular path. Circular motion, uniform circular motion. Why uniform circular motion? The hint comes from here. Remember, it cannot change the speed, it can only change the direction. So if the force acts only changing the direction and only keeping the speed constant, so obviously it will go round and round and round, and that's it. It will go in a uniform circular motion. That small derivation gives you the radius as mass of the charge, speed of the charge upon the charge into the magnetic field, and the time taken for one revolution is 2 pi m by qb. 2 pi m by qb. Okay, so that's the time taken to cover that circular motion. That's what happens when the velocity is perpendicular to the field. You can see field is inside the plane of the board in this case. What happens when the charge is not perpendicular, nor parallel, nor anti-parallel, maybe at an angle to the magnetic field? Then when it is at an angle, then it basically goes round and round while moving forward. Imagine something is going round and round and it is moving forward. That is helical motion, helix, spring-like motion. Something going round and moving forward. Visualize that in 3 dimensions. So as it goes round, it is going in a circular path just like this. So the radius formula is the exact same formula which you got over here, mv by qb. The time taken to go in that circle, same formula as you have got over here, 2 pi m by qb. So there is no difference in the formulas over here. It's just that imagine this circle is coming slowly towards you. Imagine this circle is just coming slowly towards you. That is your helical motion. But there is one extra formula which comes over here. So as it goes round and round, it completes one round, but it does not come back to the same point. It would have gone slightly ahead. How much does it move after one rotation? After one rotation, how much has it moved? That distance is basically called as the pitch of that helical motion. And that pitch is the velocity's cos theta into the time period. So your velocity might be like this, maybe, and your magnetic field may be like this. So your theta is basically this particular angle. So V cos theta into the time taken will give me the pitch. Very easy to remember. Distance is speed into time. Distance is the pitch, speed is V cos theta into the time. That's the formula for that. You can see many times questions have been asked on Lawen Force. What are the different trajectories? So very standard questions have been asked again and again and again. Okay, you can see over here, right? So these were the questions, my dear warriors, and these were the concepts which I have quickly revised for you. I will share the handwritten notes in the Telegram channel, so make sure you are a part of the Telegram channel along with these questions. At least do these questions. At least some marks will be 100% secured in your midterm, physics examination. Okay. All the very best. Now we will have many more problem solving questions classes, as well as previous year questions, as well as higher order thinking questions. We will try to solve them in the class itself. Okay. All the very best. Thank you for liking. Thank you for sharing. Bye bye. Hasta la vista.